Hello, my name is Julia Stojanovic. Today we will discuss learning from data. When discussing artificial intelligence or AI, we usually make a distinction between AI systems that operate according to predetermined rules, such as Roomba, the smart vacuum, and those that learn rules from data, such as a self-driving car or a chess-playing AI. This distinction is not strict. In fact, most modern AI systems combine rules that are specified at design time with some form of learning. Today we will see examples of rules and we'll discuss how machines learn them from data. Suppose that you are asked to design a smart light system, an AI that decides when to turn on the lights in your house and when to turn them off. How should your AI decide when to take these actions? We can start our design process by postulating a simple rule based on our own everyday experience. We will call it Rule 1. Turn on the lights when it's dark outside, otherwise keep the lights off. Recall that an algorithm is a sequence of steps. Well, our algorithm is very simple. It's just this one rule. The input to the rule is whether it's dark outside. The output is whether to turn on the light. This rule is simple, but is it any good? Does it appropriately capture how you would manually operate the lights in your house? To check whether it's any good, let's run an experiment. We will collect observations about whether it's dark outside and whether the lights are on in the house. For each observation, we will check whether the prediction made by the rule in fact matches what we observed. Let's start our first observation. We'll call it observation A. It's dark outside and we are watching TV, so we left the light on. Our rule works correctly. Let's take our next observation. We'll call it observation B. It's dark outside and we're eating dinner, so the light is on as well. Our rule works correctly again. On to observation C. It's bright outside and so we left the light off. Here too, our rule works correctly. Finally, let's consider observation D. It's dark out and we're turning in for the night, and so have turned the lights off. But according to Rule 1, we predicted that the lights should be on instead. Our rule fails on observation D. Let's look at what we've learned about the performance of our Rule 1 from our experiments. Our rule guessed the output correctly in 3 observations out of 4. That's the rule's predictive accuracy, 75%. Let's fix some terminology. It's customary to refer to the input of the rule, whether it's dark out in our example, as the input feature or just feature. And the output is usually called the outcome or the label. We went over each observation and checked whether the outcome matches the prediction. The rule we are working with is called a classifier. It chooses to which outcome class to assign an observation. The classifier we designed can make one of 2 choices. The lights are either on or off. We call such classifiers binary. Back to observation D, the one where the classifier predicted that the light should be on, but in fact the light was off. What's the cost of this mistake? As you probably guessed, it's that the smart light woke you up in the middle of the night. What can we do about this? If we compare observations A, B, and D, we see that they have the same input, that it's dark out, but different outputs. This makes us think that we need some additional features to come up with a better rule. And so a decision that you, as the designer of this AI, have to make is, what are some other input features that may be useful? These have to be features that you, based on your experience, have reason to believe will be helpful in guessing the outcome. So what should these features be? The outside temperature? No. The price of tea in China? No. Well, what about whether it's bedtime? Let's refine our rule. We will call it Rule 2. Turn on the lights if it's dark outside and it's not yet bedtime. Otherwise, keep the lights off. We will conduct another experiment, collect some observations, and then we test our rule, comparing the outcome and the prediction for each observation. And we will see that the rule is making correct guesses. In fact, we get perfect predictive accuracy. Our rule was able to guess the outcome correctly 100% of the time. And it's even turning off the lights for us if we fall asleep on the couch. So caring. To recap, what we've done so far is we've constructed a rule using our own common sense and everyday experience. We tried it out, saw that there's room for improvement, decided to collect additional information, refined the rule, tried it again, and were finally satisfied with the predictive accuracy. In fact, we are so happy with our smart light, with how convenient it is, and how it's helping us conserve energy, that we want to offer it to others to use. Let's see if it works for our friend Anne to use at her office. But before we go ahead and rewire Anne's entire office building, let's collect some usage patterns to see whether our rule would work. You know the drill. We collect observational data and ask our rule to make a prediction for each observation. Oh no! Only one correct guess out of 4. Assuming that the light is on about half of the time, this is worse than making a random guess, which would be correct half of the time. So why is the accuracy so low? The dataset on which we tested the classifier represents a different situation than the dataset on which we trained it. We trained the classifier at home, but Anne tested it at her office. And so whether it's bedtime or if it's dark outside doesn't matter much. What matters is whether the office is open. What is the cost of a mistake? The cost of a false positive, of unnecessarily turning on the light, is that we waste energy. The cost of a false negative, turning off the light when it's needed, is that people are interrupted at work and their productivity suffers. What should we do? We should go back to the drawing table, think about what additional features to use, collect that data, design an experiment to check whether our rule in fact works. But this is tedious. And most importantly, it will be very hard for us to continue deriving these rules that are getting more and more complex, depending on where the smart light is used. At home, at an office, at a hospital, at a cafe. These locations have very different requirements, and we may not know upfront what the usage patterns should be to come up with accurate classifiers. The answer is to learn the rules automatically from usage data. This allows us to overcome the limitation of relying on the common sense and everyday experience of the rules designer, and to supplement it with experience of everyone else who works, lives, or hangs out at that location where we want to install our smart light. By taking historical observations as input, and with access to some additional informative features, we can ask the machine learning method to pick up the statistical patterns, learn the rules. For example, we may derive fairly complex rules that tell us to only turn on the light if it's a workday, not a weekend or a holiday, and only during business hours, and also to skip every other Friday during the summer and to turn the lights off earlier on days that are immediately before a long weekend. By observing historical usage patterns at Anne's company's international offices, we can figure out, based on historical data alone, when the national holidays are in those countries, and keep the lights off during those days. But just as we designed experiments to check whether the rules we came up with are any good, so too should we design experiments to test, in much the same way, whether the rules that are automatically learned work well when deployed. This is because what rule is learned fully depends on historical data. If that data is representative of future use of the smart light system, then the rule will work well. But if the actual use case is different, then the rule will make lots of mistakes, turning on the light in empty office buildings and waking up your toddler in the middle of his afternoon nap. Whether the rules are written down by humans or learned from historical data by machines, we should be sure to use the scientific method, which always starts with an observation, is followed by the formulation of a falsifiable hypothesis, one that can be proven false. Next, an experiment is designed to check whether the hypothesis is falsified, and if so, we refine the hypothesis, design a new experiment, rinse and repeat. As the philosopher of science Karl Popper famously said, a theory or idea shouldn't be scientific unless it could, in principle, be proven false. The crucial question, does the classifier work, is formalized as, are the classifier's predictions more accurate than a random guess? This is the lowest bar for accuracy. You don't need a fancy AI to be flipping coins. When we have ground truth information, whether the light indeed should be or should not be on, we can check. And if the hypothesis is falsified, meaning the classifier doesn't work, it's not better than a random guess. We don't use it. We design a new data generation procedure and we retrain the model, learn a new rule. Importantly, even with this additional sophistication, it is still unlikely that we'll see perfect accuracy. One of the reasons for this is that there's uncertainty in the world. And another is that rules are sometimes broken. People may come to work over the weekend or stay at work longer to meet a deadline. And so the best we can hope for in real-life situations is that the classifier will work most of the time. But once in a while, someone will need to get up and turn on or turn off the light. Thank you very much.